Okay, let's get going. So last time we ended off talking about this one right here, and we used our definition of how a magnetic field applies a force on moving charges. And we were able to show ourselves that this thing here is going to rotate. And so we want to spend a little bit of time looking at this a little bit more in depth, this idea. So this is a magnetic field making a current loop. So it's a loop of current rotate. And so this would be the sort of more complete definition of this. So there's a torque. If you remember from last time, we ended up with a force on this side and a force on this side. If you do your right hand rule on this side here, my thumb goes with the current, my fingers go with the magnetic field, and the force is in to the page. So it was like this over here. So kind of a force going like that. And over here, there was a force coming out of the page. So you want to make sure, so again, your thumb goes with the velocity of the current, your fingers go with the magnetic field, and your palm points the way of the force. And so if you look at this picture, this is just kind of looking at it from the underneath vantage point. So kind of like looking at it from here, the same sort of picture. And you can see that, so there's this force up like this and a force down like this. In the video, we calculate that if you go through and calculate the actual force using stuff from 2A, you get an equation like this here. So it's the torque is the current, the area of the loop. So that's a nice thing. The B field you're talking about, and then sine of this angle. So this is another one of those deals where the angle is really important. It's the angle between this B field vector, which we're going to talk about in a second, and the B field that's external. And so another way to visualize this, which will be the way that you'll probably want to visualize it on a test or something, is that what's happening is a little loop of wire is a little magnet. And what this torque does is the torque wants to line up the magnetic field of the current loop with the external magnetic field that's around it. And so that's the way that's usually easier to think about it. But if you're, and the thing is, when we do different pictures, it'll be a little bit more difficult to visualize it this way, but at least hopefully this way makes sense. So we're sort of starting with that same principle of the fact that a charged particle feels a force in a magnetic field as our definition of this. But also hopefully it makes sense that the magnetic field wants to line up. So this little current loop is just like kind of a compass needle. And so if there's something else acting on it, it's going to want to line itself up with the magnetic field. Just one thing is sometimes you'll see this equation with an N in there, and that's just the number of loops. And so what somebody could do is, suppose for some reason they want to use this effect of this torque, what they can do is they can put a whole bunch of loops of wire, okay, and if you look at things like generators and stuff, usually there's a bunch of loops of wire because it makes this torque greater, okay, so something that they'll do with the electronics. And it's just the kind of thing that, in a problem, they might say there'll be 300 loops of wire, so you just end that in. So basically, if there's, this much torque for one of them, and you have 300, it's just 300 times that to be the total torque. And so let's look here then. So I'm trying to tell you that a loop of a wire with current going through it, okay, is a tiny little magnet. So if that's true, we should be able to figure out the direction of the magnetic field. So here's a square loop of wire, carries a current I that's going counterclockwise as shown. What is the direction of the magnetic field from these wires at point A? So talk about this with your neighbors and we'll discuss. Okay, so we've had some time to vote, and the good news is the majority of us have it, so that's good. I agree with the majority that it's out of the page, and something like, most of us have that too. So that's good. So let's just go through, and for the people who are still a little bit mixed up on that, talk about this. So here's this picture. And so what you can do is just go back to how we were talking about our right-hand rule last time for currents and a wire. So like right here, the way we figured out the magnetic field from a wire is, okay, if my thumb's going with the current, then my fingers curl in the direction, again using my right hand, of the magnetic field. So the magnetic field for this bottom one will be coming out right here and going in over here. And if you do this for all the 4 cases, that's the general trend. So it's coming out when you're inside the loop and going in when you're outside the loop. Okay, and again, that's just this right-hand rule. We're going to talk about them all in a second to kind of clear things up, because I know there's a lot of confusion. But your thumb goes with the current and your fingers curl the way the magnetic field does. And so if you see that, then what happens is the field will be pointing out of there. Okay, so sort of like that picture here. And so I'm just going to kind of reference these 2 pictures. So we'll do a lot of discussions of loops as we go today. And so basically this loop here, so the magnetic field is going to be coming out of it. And so it's going to look, if the magnetic field would be like sort of if you looked at the magnetic field line, if you were sort of looking at the loop, it would be pointing out at you, okay, from that loop. Now here, this is sort of looking at the side. So this view is sort of like taking my eye here and looking from the side of it. Okay, so that's this view over here. And so if I look at the side, the current's coming out over here and going in over here. And that's just saying that the current is coming out here and coming in over here. And so the magnetic field line, again, is sort of pointing in this direction. What that means is that this is like the south end here, and this is the north end. Okay, so the vector is pointing out and sort of inside the magnet, that sort of direction will be from pointing to the north up over here. Okay, so we're going to reference these pictures because we're going to do these pictures a lot. And these are, like I was saying, again, the same theme with magnetism is it's tricky because there's like 3 dimensions to it. Okay, so I think that's totally what is going on here. And so we used our curly right-hand rule from last time to do this. And here's just sort of a picture. So literally, if a little, and this is the kind of picture we're going to use, which I think, can be confusing. The idea here is this is like a little circular wire loop that someone, cut in half with like a really sharp knife or something. And so the current is coming in over here, coming out over here. And if you were to sort of, continue that, this is the magnetic field lines that it makes, which are very, close to the magnetic field lines made by some permanent magnet. Okay, and so these things can be treated the same way. We call this a magnetic dipole, right? Because it's a combination of north and south. Of course, we never can separate those, so this is sort of our fundamental thing in magnetism, but that's okay. And so this, again, looks very similar to this, and we're going to talk about this. And for anything that we do in class where we're showing you magnetic fields, we almost always do this here. Okay, it's much easier to sort of make a current and control the current to make our magnetic fields than it is to have a real one. But of course, they work in the same sort of, they work the same and that kind of thing. And again, here, if you're doing this, so we're going to learn a new right-hand rule sort of talking about this, but it's the same picture as down here. Okay, so there's the coming out there, the coming in over there, and so the same sort of north and south. So that this is, it works exactly the same way as like this permanent magnet does over here. And so our new right-hand rule, and this is just to find the B field for a current-carrying loop, your fingers go in the direction of the current, and the thumb gives the direction of the B field. So if I take my fingers and kind of go around that loop, my thumb points out of the page. This is a new one. It's sort of extra if you like the way we figured this out before. You don't necessarily need this one, but we do so much, we're going to do so much of dealing with current loops that I think it's sort of nice to have it. And so like over here, again, it's the same sort of idea. If my fingers would go with the current, So it comes in on the bottom and comes out up on the top. My thumb is over here. My thumb will be like the north side of a picture like this. Okay, and so we'll do lots of visualizations where sometimes you're looking at it from the top, and sometimes you're looking at it from the side. And so here, this one's kind of easier, and my fingers go with the current. My thumb points out at you guys. The side view, my finger goes in over here and comes out over here. My thumb is on the top side, so that's where the north would be, over here. Okay, so we're going to do a lot of calculations, thinking about things in terms like that. Questions on the pictures? I know it's, like I said, difficult to visualize. Yeah? In this particular version, yeah, thumb will always be, so where your thumb is pointing would be like the north side of the magnet for this magnetic dipole. Yes? Other questions? Okay, so let's just go in and do some examples. Okay, so there's a theme, or there's a lot of confusion with the right-hand rules, so we're going to go through and try to talk about those. So here's the original right-hand rule from last week. It's the flat one, all right? And it says the direction of force, so it gives the direction of force when there's a charge of current moving in the B field. So there's really sort of two ways you might want to use the right-hand rule. The first way is if you're dealing with a force. And so this is the one that has any sort of discussion of force, you're going to end up having to use this one here, okay? And so that's, on my equation sheet, I would probably put that down, the force right-hand rule, flat F, it's kind of like that. And so here your thumb goes with the velocity of the positive charges, your fingers go with the magnetic field, and your palm points the direction of the force. So in this particular case here, the force would be out of the page for this, this setup here that I drew. And then there's the curly right-hand rules. Okay, so this one here we just learned. So the current, my fingers go with the current, and it points out of the loop like that. And then the other one, which gives us the direction of the B field if we know the current. And so these ones are related. In a sense, you don't need both of them. You could use one or the other, but I like to have both myself. Again, we don't care what you guys do. You guys do what you think is easiest for you. But here, my thumb is with the current, and my fingers do the magnetic field. So these two rules are exactly opposite. Like in one of them, my thumb is the current, my fingers is the field. And in the other one, my fingers is the current, and my thumb is the field. All right? But so just so you kind of recap. Jeez. Pardon me. Okay. So questions on that, anybody? Okay, so let's go through and do some examples maybe. One comment, I won't really use this much, but your book will use this. So I just wanted to kind of just define it, and you'll see this is a common thing. People will define the magnetic moment of something. And so it's this little mu naught, and it's basically from that equation we were just doing, it's just a slick way to write this equation. So basically getting rid of the I and the A and calling it a mu, okay? And so it's this little thing, it's a little mu, and it's similar to that time when we used P to describe the electric dipole, and so this is just the magnetic version of that. And so this AI is the area of your loop, which here would be some circular area, times the current. And the direction is it's the same direction as this right-hand rule here. So the direction would be the same sort of setup you have here. So it gives us the same kind of picture. Like again, we won't use it much in class or on quizzes, but I just wanted to make you familiar with that so you're not kind of like, what is this thing? And it's the same sort of idea. If you're really far from a magnetic dipole, it's kind of hard for you to know what the actual sort of size of the area is and the current, and so we sort of combine them into one piece. Just to make it kind of easier to deal with. Okay, so let's test this now. So this, again, can be tricky. So here we have a regular magnet hanging out here, north and south, and we've got here a loop. Again, it's this sort of circular loop that we've cut in half with a really sharp knife, and we're told that the force on the magnet is this way, and the force on this dipole loop is that way. And so I want to know is which way is the current going in this loop here? Is it coming in at the top and going in at the bottom? Or, I'm sorry, out at the top and in at the bottom? Or is it out at the bottom, in at the top? Okay, so you need to use some right-hand rules here. So give this a try and see what you think. Okay, so looks like people have voted, and so let's go ahead and just sort of see. So basically, again, this magnetic dipole makes ourselves a little magnet. And so the way I would look at it is something kind of like this. You can make a little magnet out of this. And what's happening is these are repelling each other, which tells us that this should be the south end, and this should be the north end. Okay? So I think hopefully everybody can sort of get that idea. And then we've got to take that and apply this idea of our new right-hand rule. And so here, again, the way that we're doing this is our thumb will be where the north is. All right? And so my thumb is on that N, which means my fingers are going in at the top and coming out down at the bottom. All right? That should be what we get. And again, this is related to the one you guys had yesterday. So in at the top and out at the bottom. And so if I was to draw this, it'd be like a little dot here, and then like an X over here. Okay, is how I would represent that in that case there. And I think when I did this, it was roughly like 70% of us or something. So now it's up to 85, sort of got that. But there were still some people who were doing the A one, which is basically the reverse there. So anybody want to ask for clarification on that? Again, I think this is primarily just visualizing 3D type stuff, but yeah, question.
So why couldn't we apply the first early, right?
You totally could, right? But it's just, and so in that case, what you'd be doing is so how did you do that? I mean, I guess what you're saying is you did that and it didn't work. Is that what you're saying? So. Okay, so first of all, I got to stop. The pictures I drew, that's probably the buzz we heard. The picture I drew is opposite of what I said, so apologies on that. So in at the top would be like this, so let's just be careful, and then out at the bottom would be like that. So that's the first thing, so mental typo. So like I said, this stuff is tricky, right? So now if we're doing like that, okay, so I think your method would be like this. So he's asking, why can't we use the other right-hand rule? And the answer is you should be able to. And so like here, if this wire is coming out, then my finger should sort of curl this way, which means the north is that direction over there. Does that make sense? And it should be the same for the one up there. Okay? Questions on that? Anybody else? Like I said, this definitely is really difficult to visualize, so it takes some time. Getting some practice is really key. Okay. And then this is right along with the one from the last time. So this is the one you guys, I think you guys had this, one of these two last night. I can't remember which one now. But does the bar magnet attract, repel, or have no effect on the loop? Well, if you look at this, it's the exact same picture that I just drew. And so if you use your right-hand rules on this one, you get a situation like this. So that should be the north, that should be the south. And so these two things should be repelling each other. All right, but it's literally just the exact same picture in that last one. So it's not sort of a new example. Questions on that, anybody? And again, either one of these right-hand rules should work. It's just kind of a question of which one you want to use or how many you want to kind of think about. All right, let's do a new one. Just again, get some more practice. There's still like 30% of us that didn't get that last one right, roughly. So the diagram below shows slices. Again, so two current loops that are sort of cut in half by a really sharp knife. Think about the force exerted on the loop on the right due to the left. So the force on the right loop is directed which way? And so we're trying to find the force that would be acting on this right loop here. What is the direction of the force on this loop? So what do you guys think? Okay, so let's look at the answers here. What everyone got. So I agree with the majority so far. Again, there's still like, it's about 70% are getting it. And so I agree with to the left. And so if we look at this here, again, it's sort of a similar picture. If I look at these two loops, I'm going to get a north and a south for this guy, kind of like that. And the same picture for this one, because they're in the same direction. So north and the south for that guy. All right? And so if you got the south and the north next to each other, that's going to be attractive. So therefore, the force on this guy will be, to the left, attracted by that other magnet. So again, a lot to unpack in these problems there, but that's the general idea. So the two loops that are sort of going in the same direction next to each other will attract each other. And I think this is the same orientation the ones we just had too. So it's basically going in at top, coming in at the bottom. So I would say north points that way. So my thumb is on that side for both of them. And so that's how I would think about that one. But again, you can do it other ways, totally fine. Questions? And so you want to think about these little loops as being little tiny magnets, which is what they are. And in fact, permanent magnets are just caused by this same idea. We'll talk in a little bit just on the atomic level. So this really is kind of the unit, the fundamental unit of magnetism is some sort of a current loop like this. So how is current through a solenoid different from a current through a wire? And so we're going to see, so we're going to talk about solenoids in a second, but a solenoid is just a bunch of curled up wires. So you can treat a solenoid as just a bunch of little current loops like we've been just talking about. So we're going to see that there really is no difference. It's just that when you put a bunch of them together, it behaves in a more uniform fashion. Okay, but we'll try to hopefully explain that as we go along. What's the difference between a B field and a B field line? So the magnetic field, the B field, is this thing that's in space. And again, it's the same idea. If I'm a current loop, I create a magnetic field in the space around me. And then I can apply a force, via that field on other moving charges. Okay? And so it's the same sort of idea. What's the difference between the electric field and electric field lines? We use the B field lines to describe the magnetic field, similar to how I did with the electric field lines. So the lines represent the magnetic field, but they aren't the same thing, right? But they're sort of our visualization of it. So a lot of times we'll sort of use them as our way to kind of think about the magnetic field. And so they're really helpful with that. But, they are sort of a different idea. Unless solenoids have the same properties as loops, it seems that solenoids aren't covered in the, I'm not sure. So sorry, I'm not sure. I think they're in there, but maybe they're not. I also think I mixed up the order of the videos. I don't know if anyone noticed that. Sorry about that. So that was probably confusing. But a solenoid, again, it's just like putting a bunch of loops together. So it really does inherently have the same properties. And then basically the number one comment, just in different ways, was I'm still confused as to the right-hand rules, okay? So that's definitely, I think a lot of us, it's still, like I said, 30% are still seem mixed up on this. So we're going to try to get some practice today and some practice in discussion and then put up some problems and we get the practice quiz up for next week soon. So I think just getting some practice will hopefully help with that. But I would definitely sort of have that on my equation sheet and kind of start writing it out now. Any other just questions about the lecture or anything before we carry on? Okay. Well, so we're getting near the end here. And so this is for a trip to the Final Four. Okay, so here's the Game of Thrones, Parks and Rec, Breaking Bad, and Atlanta. So here we go. Tough one, huh? Okay, this is your last chance. I'm going to call time here. All right. It's close. Oh, Parks and Rec. Sorry, it was a good try, but this, of course, is one of the powerhouses of April Madness, right? All right. Ooh. All right. So again, for a trip to the Final Four, this one was kind of a beatdown. Sorry, Atlanta. Better luck next year. More people said, I don't know the show than actually picked Atlanta. Sorry, Atlanta. Okay. So again, this is a trip to the Final Four. So our first two entries of the Final Four are Breaking Bad and Game of Thrones. So catch us soon to finish that up. So there's lots of things we're kind of winding down. All right. Solenoid. So as we were talking about, solenoids are basically just a bunch of wrapped up current carrying wires. So they're very similar. I mean, hopefully you can see that similarity and use it effectively to try to understand them, but it's just literally taking a wire and just curling it up a whole bunch of times. Okay, this is sort of our easiest way to make what is really close to a constant magnetic field. And so in that way, the solenoid is the analog of the capacitor was when we talked about electricity and electric fields. So the solenoid makes what's essentially a very constant magnetic field inside of itself here. But again, like a capacitor, it's not exactly perfect, right? It's sort of the sort of longer these things are, right, and sort of how tightly the wires are. But it's a really good approximation. And so we're going to use that approximation in class for this idea of a solenoid. So it's just a fancy word for just a bunch of, and you can, again, picture it as just, we just sort of talked a bunch about one current loop. Well, now it's basically having 15 of them in a row or something like that. And so you can imagine that just sort of magnifies the total number or the total size of that magnetic field, and then, of course, makes it more uniform. So here's our equation for the magnetic field of a solenoid. And we'll see where these come next time. We're going to talk about Ampere's law, which is kind of the magnetic field version of Gauss's law, in that we'll be able to use it to calculate some of these magnetic fields. You'll see where some of these equations are coming from better. But this is the one for the magnetic field. And again, like the capacitor, it's constant, right? As long as so if we got this constant guy, mu naught, then the current going through the loops, and then N is the total number of turns of wire. So you would literally just count these little turns of wire here, whatever they are, divided by L, the length of this thing here. Okay. Now, this is another thing where if you look around and find different things, people will define this a little bit differently in that sometimes you'll define what's called lowercase n, which is that n divided by L. So you'll see some people call the magnitude of the magnetic field to be U naught I times lowercase n. Again, it doesn't really matter, but both of these are just the same thing. But it's a nice constant magnetic field. And again, the things that it depends on is the current, and then this ratio of sort of how tightly packed these wires are. So it's the turns of wire divided by length L. So let's do a couple examples looking at this here. And so we have solenoid 2, which is the one on the bottom, has twice the diameter, twice the length, and twice as many turns as solenoid 1. How does the field B2 at the center of solenoid 2 compare to B1 at the center of solenoid 1? So think about this. We got two different solenoids. We just talked about this definition here. How would these compare? Okay, Let's look at this one here. This one is, I think, kind of tricky. And so let's see what we think. Let's just kind of define some of these things. So first of all, by diameter of the solenoid, we mean this thing right here. Okay, so diameter of the solenoid is basically, the solenoid makes a little circle with these wire loops, and so that would be the diameter of it. However, though, if you look at our equation, what is our equation? So our equation is this mu naught I big N divided by L. Okay, and so we're sitting here, we want to compare the magnetic field. Now in this problem, we're told that the current is the same. Now it's sort of really tiny here, but still you can see it's the same current. And so it comes down to this ratio of N divided by L. But what do they say here? Well, they say that solenoid 2 has twice the length. Okay, so the L is bigger, but it's also got twice as many turns as solenoid 1. And so basically there's a 2 and a 2 up there and down there, and they cancel out so that the magnetic field is constant in this case here. Okay, so it doesn't depend on this diameter at all. Okay, it only depends on the number of turns, the length, and then the current. And so in this case here, because those happen to work out exactly off by a factor 2 for both of them, it worked out. So questions on that. So that's a tricky one. I think just getting kind of used to, the idea here is just kind of get used to what these things mean here a little bit, I think, hopefully. And then now the other thing that we'll use probably more often than not is how to relate the current in the solenoid to the direction of the magnetic field it causes. So here, in this example, we've got the solenoid and we're drawing the magnetic field lines. And so I want to know is which way is the current going through this solenoid? Is it coming in on the right, coming out at the left? Is it the opposite? Would either one of these work in this case? What do you think? Okay, so I think that's most everybody now. And I think we agree, the majority agrees with me, but again, there's still a little bit of confusion. So let's talk about this. So I would say enters on the right and leaves on the left. So it comes in here. So the current comes in here. And then I would say it comes out over here. And again, you want to connect this. When you're thinking about the direction of the magnetic field in the solenoid, you can just use these same rules we were just doing. And so here, if you look at this one here, if I take my fingers with that current kind of coming up and circling around, then the magnetic field points this way. And those lines, the north would be on that side over there. Okay, so you look at the lines from a permanent magnet. This would be your north side. This would be our south side. Okay, so this is the way these lines generally trend. But of course, if you just do your curly right hand rule, if you come in on this side and curl around, your thumb points that way, which is what you want. You can also do it on the other side over there, but it's the same sort of idea. And so this is important. So we'll definitely use this from time to time. It could be, again, sort of figuring out the direction of the magnetic field of these loops and these solenoids. Definitely something we'll be doing a lot of over the next couple of weeks. Questions on this one? Right, and so here's, again, the magnetic field outside a solenoid looks like that of a bar magnet. Okay, and so if you sort of look at them, again, it looks the same as a bar magnet. And again, if we're doing anything in class with magnetic fields, we're almost always using a solenoid or some kind of wired loops or something like that because you can control it easier than you would the bar magnet. So here's, a lot of times if you're doing some sort of medical procedure that involves a magnet, you'll find it, you can sort of see where the solenoid is somewhere. So here for an MRI, the patient is sitting inside a solenoid. That's how they make the magnetic field. All right, and so this is, again, for most things where you're using a magnetic field, a solenoid or current loops or something like that is generally going to be what's involved. And so just to kind of follow up on some of the stuff we've been talking about. So again, there is no magnetic charge. Our fundamental unit of something that causes magnetic field would be like a little current loop, a little magnetic dipole. And so where is the moving charge in, say, a permanent magnet? Well, there's two sort of places we get this, but it's essentially the movement of electrons about the nuclei. Now, you guys have probably been in chemistry classes or maybe heard this in other physics classes. When you get down to that atomic level, it's not as simple as the electron just sort of orbiting around, kind of like, the moon orbits around the Earth. It's different than that. So there's a lot of quantum mechanics involved when you get down and try to sort of describe these things. But basically, this picture is a helpful picture in just kind of understanding the origin of where this magnetism comes from. And so for one situation, you can imagine this electron sort of literally as a little current loop, okay, sort of looping around the nucleus with some I. If it's moving around, then there's current moving versus time. And so that's one source of magnetism from atoms. The other one, which is actually the stronger one, is again the spin of the electron, which most of us have probably heard about. Is again another thing that's really complex. Now, this is not, it's not like the electron is actually spinning. We're not even really sure what an electron is when you get down to it, right? But if you can just sort of picture that idea of a spinning top, right? That again is moving charge. If it's a charge, it's actually moving. And so these atoms with an extra electron, so these ones that don't have a sort of paired up two extra electrons will be the ones that will be your culprits for something that might be magnetizable, okay? But this is sort of the bigger picture of this. And so generally what happens in materials is you can kind of think about, so suppose there is an atom that has a magnetic moment. So basically has an extra electron that maybe is acting like this with its spin like a little tiny magnet. Okay, what generally happens is they're all kind of random, and so they don't add up, and so there aren't actually any sort of large-scale magnetic effects caused by this. Okay. However, there's some materials, and the one we'll talk about, materials called ferromagnets, which ferro means iron-like, so iron is the big one, where they like to have their magnetic fields or magnetic moments aligned. Okay, and so if you can think of, so each little atom is like a little tiny magnet, a little tiny loop of current, and they like to actually align themselves up, okay, all in a row. And so what happens then is you can, okay, see this sort of large-scale effect more so. And the way that this typically works is in a ferromagnet, you have little domains. And domains mean there's like a little region here where all the little atoms in their current loops are lining up, say, in this direction. And the one over here is lining up in this direction. And they tend to line up in ways where they, again, cancel out. So if you find a piece of iron in the ground that hasn't been anything sort of done to it recently, it's typically going to be like this, but it won't have any large-scale magnetic effects. Okay, and what it is in order to sort of produce something like a permanent magnet, what you do is you bring in some magnet. So right here you can see these domains are pretty much kind of random, and so it's an unmagnetized piece of iron. But if you bring in sort of an outside magnetic field and put that in there, then what happens is the domains that align with that tend to grow. And so now this piece of iron is going to tend to end up having the magnetic field that this one is inducing on it. And so if you've ever dealt with this, when you're charging up like a magnet, you sort of put it in with other magnets, literally, to sort of make it magnetized. And so this would be an induced magnetic dipole, getting these things to all line up like that. Okay, and so here's another thing. So just to kind of follow up on this, so in your book, they go through the Biot-Savart Law, which is this thing here. And what this is the magnetic field version of Coulomb's law. Okay, and so it's the sort of for the magnetic field caused by a moving point charge. All right, this is our law here. It goes as 1 over r squared, just like Coulomb's law did. And what you can do is by doing this, and the book goes through some examples, you can calculate magnetic fields of different situations. But it's the same sort of idea, right? And so with the electric field, we had that situation where we could sort of add up the electric field done by a whole bunch of little tiny point charges. It's the same idea here. You can find the magnetic field caused by a whole bunch of little moving point charges. And so it's the same sort of idea. This is an experimentally derived equation. So people got it by sort of seeing the effect that magnetic charges had. And so the sort of big question that I'll get sometimes is, why does this happen? What causes the magnetic field? And that's a tricky question. I mean, it's sort of, you don't think about it the same way. People don't say, why do electric charges give off a force, right? But they will ask, why does a moving charge give off a magnetic force? And unfortunately, you can't give a really great answer without looking at relativity. Okay, so Einstein's special relativity is, and it's actually so I feel kind of bad in a class where you don't actually get to relativity, because we're sort of leaving you hanging. But when you talk about relativity, they'll bring this back up again. If you look at special relativity, embedded in it, in fact, it actually came out of Einstein thinking about magnetic fields, is the fact that in order for special relativity to be true, you have to have a magnetic field. Okay? And so you'll eventually get to that at some point. But just that question can sort of be answered that way. But for us right now, experimentally, we know that a moving charge will cause a magnetic field in this regard, similar to how the Coulomb's law tells us that a magnetic field is caused, or electric field is caused by a regular charge. So similar to Coulomb's law. So then we can start doing questions like this here. So here is a negative charge moving into the screen. I want to know is what's the direction of the magnetic field at the position of the dot. So this Biot-Savart law, you can do it on sort of one charge at a time. And so if there's one charge moving like in this case here, which way would the magnetic field from that one charge be pointed? And again, to find the direction, you use the right-hand rule like we've been using for a couple of lectures now for the direction of a magnetic field. So sort of think about this as a current. So talk this over with your neighbors and see what you think. But this is how you would find the direction of the magnetic field from just sort of one charge. Okay, so if you look here, it's one of those cases where it's some confusion, but if you think about it, most people got C or D, and so I think we'll be able to clear up that problem there. But there is some confusion on this. So let's look at this here. So the way you would do this is you would do this with our curly right-hand rule from last time. So here, the velocity goes into the screen. So you kind of can do this different ways, but if I put my thumb into the screen as the current, then my fingers will curl around in a clockwise fashion, okay? And so in a clockwise fashion, I'd end up getting some kind of a picture like this here. So this would be my magnetic field, and in clockwise fashion would be like this here. So if I just use the right-hand rule, I get that there, which would imply, right, that the magnetic field would be going up, okay? So why is the magnetic field then, in fact, going the opposite way? Can anyone tell me? Because it's an electron. okay? So it's one of those deals there where, and the thing is, I'll just give you a little bit of warning. So we do that here in this example. So on the test or anything, we'll try to be super clear about this, but any current that we call I on the test is always positive charges moving in that direction. Okay, now if we do it sort of on an electron by itself basis, we could throw that in there. But again, I want to kind of get you to see the hardest version of that. Okay, I'll be down here if you have any questions. We'll see you guys next time. Thanks.